Hello and welcome to week 4 of Advanced Quantitative Methods in Psychology. Alright, so this week we're getting into some exciting times. We're going to be figuring out how we can find where the differences are in our ANOVAs. So that'll make sense in a moment if it doesn't already. So we're looking at comparisons following a significant ANOVA. Now, in case I forget to say this, when we talk about the follow-up tests that we're going to talk about in a moment, you'd only follow up with these kind of tests if you have a significant ANOVA. I just don't want to, just in case I forget to mention it later on, if you've got a non-significant ANOVA, there's no differences anywhere, so that's basically the end of the journey for that piece of the research. Alright, I just thought all that came to mind. So we have looked at Familywise error very briefly in a previous week. This week we'll sort of unpack that a little bit more, make sure that we know it's important to keep an eye out for. And then the rest of the lecture is going to be about following up the significant ANOVA. So there's two ways we're going to do that: planned contrasts and with post hoc tests. You choose one or the other, you wouldn't do both. And we'll make sense of that all in a moment. So if you recall back to week 2, a couple of weeks ago, we found out that between groups ANOVAs compare the mean scores of more than 2 different groups. So you're looking at individual groups, not the same groups being compared at the same time, over time or anything like that. It's 3 different groups usually or more. So the null hypothesis is that the mean score of each of the groups is the same. So there's no major difference between the mean scores of the groups 3 or more, however many you might have. The alternative hypothesis then, if you've only got 3 groups, then you can list them all nicely here. So we've got perhaps the mean 1 and 2 are different, but mean 2 and 3 are the same. Perhaps mean 1 and 2 and 3 are all different from each other, or perhaps mean 1 and 2 are the same, but mean 2 and 3 are different. So the ANOVA says that something is going on, but we just don't know where that difference is, where the unequal means are. So that's what we are going to be looking at today, is how do we figure all that out. So just to recap on what we've done in the previous couple of weeks as well. So week 2 we got into really what's going on underneath F statistic and the ANOVA itself. Last week we got into looking at the assumptions. We really broke down the assumptions and a bit of bias, figuring out, looking at outliers and things like that. So we make sure that our data is in a good position to be able to run the analyses. This week we're doing some follow-up. So there's sort of 3 major sections, and this is the last sort of section of the analysis that you run. So you make sure your assumptions are alright, which is what we looked at last week. You run the actual analysis, the ANOVA in this case, between groups ANOVA. If it's significant, then you go ahead and run the follow-up tests, which is what we're going to be looking at today. If it's not significant, then you don't need to do this last step because there's nothing going on. Alright, so there are a number of options. There's 2 overarching sort of options that we'll look at. Within these there are a couple of different variations. So planned contrast, we'll look at those first. They're also called planned comparisons. They might have other names, but they're the 2 main names. So if you hear or read of anything about planned contrast or planned comparisons, that's what we're talking about here. And then we'll be looking at post hoc tests. So there's a multitude of different post hoc tests, and we'll look at the important ones of those, the ones that you need to know about. So again, we asked this question before: why don't we just run a bunch of t-tests? So you could just run a bunch of t-tests instead of running an ANOVA itself. But then when you do get a significant ANOVA, why don't you just run a bunch of t-tests to compare the groups after that? And you could do that, there is potential to do that, but the issue is that you might end up with some family-wise error. So remember, Statman in the past mentioned that we need to watch out for family-wise error. that's why we don't just run heaps of t-tests. So I told you that we were going to break this down a little bit further in future weeks, a couple of weeks ago. So this is how your Familywise error gets inflated for your tests. So for every test you run, you increase your Familywise error. So there's a little field section if you want to get into a bit more depth about this stuff. So with an alpha level set at 5, so remember, 0.05, remember the alpha level is the level that we require our P level to be below to be significant. So with an alpha of 0.05, there's a 5% chance of making a type 1 error. So there's a 5% chance that we're going to be finding an effect that actually doesn't exist in the population. So thus there's a 95% chance of not making a type 1 error. Alright, so there's 95% chance, 5% chance that we'll make a type 1 error, so there's 95% chance that we won't make one. So for each test run, there's a 95% chance of not making a type 1 error, just repeating myself there for some reason. So to assess the chance of not making a type 1 error, we can multiply this number 0.95 in this case by itself for as many tests as we do. So how many tests you do, you'll multiply it by itself. So you to the power of, in this case, to the power of 3, but this can keep going up for as many tests as you want to run. And you'll see in a moment how much that will affect your, or how much you have to adjust your analyses. So here we have 0.95 times 0.95 times 0.95. So run 3 tests in this case, 3 t-tests after our ANOVA, and now the chance of us not making a type 1 error has gone from 95% to 85.7%. Or 0.857. So there's 85.7% chance that we won't make a type 1 error. Or, since the maximum probability of an event occurring is 1, we can make the inverse of that. 1 minus 0.857 equals 0.143. I'm not going to try to break down what that all those calculations mean, because we don't really need to know it. You can either trust me that that's the case, or trust that I've read field correctly to interpret that for you guys to be the case, or you can go into field and really get your head around that if you want to get that real depth of knowledge about this stuff. So for running 3 t-tests to follow up our ANOVA, we now have a 14.3% chance of making a type 1 error, of finding an effect when there actually isn't one in the real world. So I think previous weeks we mentioned that it's approximately, you can keep adding 0.05 approximately to approximate the percentage. So in this case you'd have 0.05 times 3, so you'd end up with 15% or 0.15. So that's the other way. This is the more accurate version. That's the actual percentage that you'll be looking at, but you can sort of eyeball it pretty quickly by just adding up your percentages, if that makes sense. But again, take-home message here, we don't have to make these calculations ever, but we do need to be aware that the more t-tests or the more analyses that we run, unless we're making adjustments for them, we're going to have to adjust our expectations based on the percentage of making a type 1 error. Alright, so that's why we don't just run heaps of t-tests. We just inflate the chance of making an error. And here we go, if we have 95, so if we run 10 t-tests, so 0.95 to the power of 10, we end up with 0.599, so 59.9% chance that we won't make a type 1 error, or 40.1% chance that we are going to make a type 1 error. So there it's, with 10 t-tests, you can see it's jumped up to nearly 50-50 chance of making a type 1 error, which means that our tests are pretty useless. We could go one way or the other, and with nearly the same amount of probability. So you can see how it can jump up pretty quickly. So here we go, I just said this. We don't have to be able to calculate this stuff, but do be aware that you don't want to run t-tests over and over and over again on the same data, because you're going to inflate your chance of making a type 1 error, and it's going to make your research look very poorly. So how do we figure out what means differ in an ANOVA then? That's where these next exciting little tests come in. So there's two main types, as I said before. So there's planned contrasts and there's unplanned comparisons, or planned comparisons or unplanned comparisons. So planned comparisons are also considered as a priori, which just basically means that you've come up with this before, prior to running the analyses. So planned contrasts are based on theory or logic, and are used to test differences that the researcher has in mind prior to conducting the research. So an example of this might be, thinking about the puppy treatment that we looked at a couple of weeks ago, I think the puppy treatments are going to make people happier than the control condition. So that's when we just talk about all the puppy treatments together are going to be better than control condition. And then I also think that the 30 minutes of puppies therapy will produce happier results, or that's not very good worded, but will produce better results than the 15 minutes of puppy therapy. So basically here we're saying, with this idea, we're saying that the control group is going to be worse than the other two groups put together, and then the 30 minutes is going to be more effective than the 15 minutes in affecting our happiness scores. Alright, so that's an example of how you might go into a study and expect a certain outcome. So I mean, that could be based on, you could say it's potentially based on theory, but really it's just pretty logical that you've got your control group in there to show us, to be able to have something to compare to make sure that our therapy is not just having the, or it's not just something else that's going on which is having an effect besides our therapy, and then the 30 minutes versus 15 minutes is just to see if it's sort of a cumulative effect, for example. So that's an example of a planned contrast, or a couple of contrasts in that case. Unplanned comparisons are usually referred to as post hoc tests. So I say unplanned comparisons, but really most of the time we're going to call these as post hoc tests. So post hoc just means after the fact, basically. We're just doing a bunch of tests after we've run the analysis without anything in mind, really. So these test all possible combinations of pairs. So this might come down to someone saying, I'm not fully sure where the differences might be, so I'm just going to test every possibility. Or perhaps they're just saying, I'm interested in finding where any differences might be, so I'm going to test every possibility. So it might be that they're just unsure of where it might be, or it might be just that they're really exploring the data and they want to find out if there's differences in places where they might not have expected it otherwise, or they have no theory to really give them strong inclination towards one or a limited number of hypotheses. So a little quote from old Fieldy boy. Typically planned contrasts are done to test specific hypotheses, whereas post hoc tests are used when there are no specific hypotheses. So that's summing it all up nicely. If you have a hypothesis, then you're probably better off doing planned contrasts. If you're fully exploratory, or you not really sure where the differences might be, just do some post hoc tests. Cool. But what are these things that we speak of? So planned contrasts, good thing about these, they can reduce the amount or even remove the need for making adjustments for increases in Familywise error. So remember, the reason we do planned contrast or unplanned comparisons or post hoc tests is because we need to take account for the Familywise error that might be occurring from these multiple tests. So we still do, sometimes we can just not have to make any adjustments, so the only real way you can do this is to do some orthogonal planned contrast, which we'll talk about in a moment, and then you don't need to make any adjustments at all. Otherwise, if you do post hoc tests, or you do a certain number of contrasts which are not orthogonal, which we'll get to in a moment, then you have to make some sort of adjustments, or SPSS will make some sort of adjustments for you. Alright, and there's the sections if you want to, it's probably worthwhile just having a good look at these sections as well. It's quite an important aspect of running an ANOVA, is knowing how to figure out what's going on afterwards. If some of the bits and pieces aren't fully sinking in, don't stress out too much. As long as we sort of get a sort of grasp of that these tests are following up the ANOVA, and how to interpret them is probably one of the more important things, and which ones are better to run in which conditions. Alright, so here we'll go with a planned contrast first, the a priori tests. So field lists 3 rules for choosing contrasts. So generally, if you have a control group or control groups, as the case might be, these are generally going to be compared to the other groups. So that's usually your first port of call for your contrast. So generally you'll compare your control group or control groups to all the other groups, all the treatment groups, wherever the case might be. Secondly, each contrast should compare only 2 chunks of variation. So an important thing here is that he's using the term chunks. So we're not necessarily just saying to compare 2 groups at a time. You'll see in a moment that we'll actually be able to compare chunks, which could be a couple of groups or several groups stuck together. So in the example we're going to have in a minute is comparing the control group to the non-control groups as one comparison. So the control group versus the puppies, regardless of how long they did it. So that's the 2 chunks we're talking about, and we'll unpack that a little bit more in a moment. So once a group has been singled out in a contrast, it cannot be used in another contrast. So we're talking about orthogonal contrast at the moment. So the unrelated contrast. And if you follow these rules, the top one's more of just suggestions, probably makes sense. It's a logical thing that you do. But the other 2 are important for maintaining orthogonalness in your contrasts. And that means that we don't have to make any adjustments for our multiple comparisons. So as long as whenever you break a group off, so for example, if we're comparing the control group to the other 2 groups, we can no longer do any comparisons with the control group because it's been singled out amongst the groups, and if we do any more tests with that group, we have to do some adjustments, so adjusting our alpha level or something like that. Alright, and that's all sort of stated below there. Alright, so let's try and make this a little bit more concrete. At the moment it's all theoretical and up in the air. I'm sure it's a little bit confusing. So let's go back to that little statement that we made before, that the researcher made about the puppy treatment. So I think the puppy treatments are going to make people happier than the control condition. So that's going to be contrast number 1. And then secondly, and 30 minutes of puppies will produce happier results than 15 minutes of puppies. So that's our second contrast. We're going to first compare the puppy treatment all together with the control, and then we're going to compare the 2 different puppy treatment lengths of time groups against each other. So this is what it's going to look like. So the first top sort of row we've got here is the actual ANOVA we've run. We run the ANOVA, we found it significant. So we know something's going on in there, but we don't know what's going on in there. So we're going to run a couple of contrasts, and we're going to talk about how you run the contrast in a moment, but this is more of the conceptual understanding of what's going on. So contrast 1, we'll be looking at control group versus both puppy groups combined. So that's when we're talking about the chunks of data, or the chunks of the conditions. So now we're looking at control groups, or the control group versus the 2 puppies combined groups. For our second contrast, we're going to ignore the control group altogether because that's already been singled out and compared. So now if we do any more analyses with that, we'll have to adjust for family-wise error. But because we're just going to leave that out of the second contrast and we'll instead split this bit into two and compare the 15 minutes with 30 minutes. This remains orthogonal. That's the big thing with orthogonal, is once you divide something up, you can't stick it back together, or you can't do anything else with it. And Field goes into talking about this like a piece of, like a big cake. Once you take one single slice out, so you take one group out, and you do an analysis of that, it's basically you can't stick that back into the cake and say it's part of the cake again. It's always going to be its own single piece of cake, and it's no longer useful unless you do some sort of adjustment. He explains that a lot better. So if it doesn't make sense and you really want to get your head around what orthogonal contrasts mean, which you probably should, it's not a bad move to make, then read up on the Field section 12.4 by the looks of things. Alright, so that's an example of what planned contrast might look like. Now this is a figure just taken straight out of Field. So this is just to show that if you did have more groups than just our control and the two treatment groups. So this is an example where we have 3 experimental groups and then 1 control group. So you do the same sort of thing. So here, the control group has been singled out. We're never going to use that again, or else it's going to be non-orthogonal. So control group versus the 3 experimental groups, the first comparison or the first contrast. Then we're going to ignore the control group from then on. And then we're going to look at experiment 1 and 2, or experimental groups 1 and 2, and compare that with experimental 3. Again, once 3's been singled out like that, we're never going to look at it again, just to maintain that this is going to be an orthogonal contrast. And then we can further do another contrast here and look at how experimental group 1 and 2 compare to each other. So here we've done 3 contrasts. And we're able to still use a p-value of 0.05 to use our criteria for a significant result. So we don't have to do any adjustment. That's the beauty of the planned contrast, and the beauty of going into a test having a theory behind it. Cool. And then another example straight from the book. Here we have 2 control groups. So there's different reasons why you do that. I'm not going to get into that now, but here we have 2 experimental groups and 2 control groups. And here we're comparing the experimental groups to the control groups, and then we can further split the experimental groups, compare them to each other, and then because there's 2 groups in this chunk here, we can still further split that and then compare the 2 control groups. Alright, so because they haven't been singled out, you can further divide them. You can keep dividing the groups until they're singled into their own groups. Once they're in their own single group, you run that analysis, and then you can't run any more analyses with that singled out group unless you make adjustments for the multiple comparisons. Hopefully that makes some sort of sense. Alright, so in SPSS, to actually run this, I don't usually go into so much depth about how to do this in the lectures, but we're going to go into a bit more depth about how this happens in SPSS, because it's all still a bit abstract by saying we're going to divide them into groups, blah blah blah, or chunks, and do the comparison. So we'll unpack it a little bit more now. So groups coded with positive, these are just some sort of rules, I guess, for doing your contrasts. So first, the groups coded with positive weights will be compared to against groups coded with negative weights. So if we're doing the control versus the 2 puppy groups, we'd give the puppy groups a positive weight and the control group a negative weight. So a weight is just a number we're allocating to them. You could do that the other way around. It doesn't matter which one's positive or negative number, as long as the positive ones on one side of the comparison are all positive and the guys on the other side of the comparison are all negative, then they'll be compared. And again, this might not make sense until we start putting it into practice a little bit in the tutorials, or when I talk about it a little bit further. But yeah, that's one of the rules. So you might have to come back to this and reread it later on to make sense of it. Another rule is assign groups you don't want in a contrast to 0. So remember the second contrast we have in an above example, we no longer required the control group to be included, so we just give him a weight, or give that group a weight of 0, and means that it will not be included in the following contrasts. And then the third rule for the weights for the contrast is that when you add them all together, it should equal 0. So you need to give positive and negative numbers in a way that means it's going to all equal 0. So this is all very abstract and weird at the moment, but we'll go through it and try and make sense of that now. Alright, so going back to our puppy example, this is what we would do. So again, we've got the 3 groups. That's our ANOVA that we've run at significant. Now we're going to do the contrast. These are the 2 contrasts that we've come up with. We're going to compare the control group to the 2 puppies groups chunked together. So the weights we'd give these guys is we'd give -2 to the control group, and 1 to the 15 minutes group, and 1 to the 30 minutes group. So the reason we put -2 here, it's not just a random thing, because we have to remember all these, when we add them together, need to equal 0. So we could also, it wouldn't make a difference to our results, we could make the control group a +2 and make these two -1 and -1. Doesn't matter which side is negative, which side is positive, it's just the positive and the negatives show SPSS which side of the comparisons are going to be. You could also, if you wanted to, make this, for example, -4 and this one +2 and +2. As long as it equals 0 and the positive ones are on one side, or the one side of the chunk is all positive numbers and the other chunk being compared to is all negative numbers, then that's all good. Alright, so hopefully that made a bit of sense. And then for the second contrast, now we're no longer looking at the control group, so we'll give that a weight of 0, and we've got the 15 minutes puppy group is going to be weighted, I've chosen to do it as -1, and 30 minutes puppy group is going to be weighted as 1. Again, you could do +1 and -1 the other way around, wouldn't make a difference. Or I could make this guy -192 and this guy +192, as long as when we add the 3 numbers up, it equals 0. Alrighty. And here's the examples of how this would look with the other examples that we had. So again, add these numbers up. So 1, 2, 3, -3 equals 0. 1, 1, -2 plus 0 equals 0. 1, -1, 0, 0 equals 0. And also the contrast, positive numbers here, negative numbers here, positive numbers here, negative numbers here, zeros for anyone who's not being compared, 1, -1, positive numbers, negative numbers for the 2 different contrasts or groups being compared. The other example we had with the 2 control groups, add them all together, equals 0, positive numbers on one side of the comparison, negative numbers on the other side of the comparison. This time for the second contrast we don't actually include the control group, so they're zeros, negative number, positive number for the different comparisons, equals 0 when we add them all together, and vice versa down here, all zeros for the experimental groups because they're not being included, positive number, negative number for the 2 different sides of the comparisons, all equals 0 when we add them all up. So I might have started talking a bit quickly there, but hopefully it starts making sense a little bit with this. Once we start playing around with this in the tutorial, hopefully it'll sink in a lot better. Yeah, so if it's fully not making any sense, it might be worth just having a look at the field section that I mentioned above, just to try and get your head around it. So this is what it looks like in SPSS. So sorry it might be a little bit messy, this slide. First thing, just ignore the windows that are open here. The first thing you want to make sure you remember is how your data is coded. So here I know that the control group is coded as 1, the 15-minute puppy group is coded as 2, and remember there was a little A1 button that we can click to swap between the numbers and the words. And then the 30-minute puppy group is coded as 3. So what we need to do, these are all in a nice order at the moment, but they might be all over the place and not necessarily in a good order in your data set. But what we need to know is what order they come in. So whoever is coded as the smallest number is going to go first in our weights when we put in our weights. Whatever group is coded with the second highest number is going to go in next when we put our weights in, and the next group, and so on and so on until you cover all your groups will go up in the numbers that they're coded with. So when you're in your ANOVA, and we should have run these already. I'm pre-recording these, so I'm not sure where we're up to in reality, but we should have run one-way ANOVAs already. There's this little contrast button which we haven't played with yet. When we click on that, so when it's all set up and ready to go, we click on the contrast button, and we start putting in our coefficients. So here you'd actually enter your term in, so it's good to write these out to make sure you know the order and all that. So I know that control group is going to be our first one, and that's going to be on one side of the comparison. So in this case I chose to give that a positive 2, because I know it's going to be compared to 2 other groups. So I put 2 in the coefficients, push the add button, then the 2 will appear there. And then I know the second group we're comparing to is a 15-minute puppy group, so I'm going to put -1 in the coefficients box, push add, that'll appear there. And then the third group I know is a 30-minute group, so I put another -1 there, add, and then this is what you end up with, 2, 1, 1. Again, add them all together equals 0. One of the comparisons, the control group, is a positive number. The other side of the comparison are the treatment groups, which are negative numbers. Alright, and then to do your second contrast, you push this next button, and then it'll go to a clear, it'll just clear the screen, and then you can put in these contrasts. So 0, we don't want the control group in there anymore, so we give that a 0 in the coefficient box. Add, we're going to put 1 for the 15-minute puppy group, add, we put it there. 30-minute group, -1, add, and then it'll put it in there. So we're only doing 2 contrasts in this at this stage. If you're doing more than that, you just keep pushing next until all your contrasts are finished. Then we push continue, and then whatever else we want to do with our ANOVA, and push OK. You can see the post-hoc. We're going to be looking at that one next, just to show you the little post-hoc button. And that's all what I just said there. Alright, so this is all probably still a little bit weird, just me talking about it. Once you can have a play around with this with your SPSS, or you can wait until the tutorial, and we'll definitely have a good play with this to make sure we're understanding what's going on. Alrighty then, so this is the output you get. So once you do all that and you push OK, this is the output you're going to get. You're going to get your ANOVA for starters, and we've already talked about this previously, how you write that up. So we've got the 2 and the 12 degrees of freedom, actual F statistic here, which we've rounded up incorrectly there for some reason. Should be the other way around, sorry. 5.12. See how easy it is to make a mistake. And then the p-value 0.025. Lucky I'm not getting marked on my slides, hey? Alright, but it is definitely a significant result, so we're going to follow this up with the contrasts. Planned contrasts. So now the next table that we look at is just to make sure. It's always good to double check that we've done the right thing. So here we can see the first contrast, control group is 2, the other 2 are -1s, which means that we're comparing control to the other 2 groups. So that's fine. Last one, control group, we'll weight it as 0, and then we're comparing 15 minutes to 30 minutes, which are positive and negative 1s. So that all looks good to me. Definitely worthwhile with contrast. Very easy to muck these up. Definitely worthwhile double checking this table in your output. And then finally you get your actual contrast. So I've made this green. It's not normally green like this, but this is just to sort of highlight where I'm getting the numbers from. So you can see we've got the assume equal variances here, or does not assume equal variances. This is when we've already done our homogeneity tests, or tests for homogeneity variances. So remember, we could be doing Levine's test or spread versus level plots or whatever we might be doing to test our homogeneity variance. So in this case, I'm just going to assume that we have assumed equal variances, homogeneity variances. And here are our two contrasts. So this is the value of the contrast. You don't really need to report anything about this one. Standard error, again, we don't need to report anything about this. This is used to make our comparison, so it's the sort of effect, the difference between the groups, and this is a standard error calculated from the variances, etc. But what we do want to make sure we report is that the t statistics, the degrees of freedom, and the p-value. So you can see I've written them all out nicely APA style across here. Hopefully I've got the numbers right this time. So degrees of freedom 12, the t statistic itself is 2.47. So t-test, you might notice that I haven't put a negative number in. There's no need to put in a negative number. You can, it's not wrong, but there's no need, because really that all just depends on which way you put the analyses in. So if instead for this first contrast we put a -2 and 2 positive 1s, then this would be a positive number. So it doesn't mean anything as far as all that goes. So I never put in the negative symbol for t-tests. Just a little fun fact as well, degrees of freedom, you know, in the ANOVA we always put in 2 degrees of freedom, one for the model and one for the residual. The reason why we don't put it for a t-test is because you're always going to have the same first degrees of freedom, which is going to be 1, because you've got 2 groups minus, so 2 and degrees of freedom minus 1 would equal 1. So you'd always put in that 1. So I guess the reason we don't put that in is because you're always going to have that 1, so no one cares about it, so we just leave it out. Little fun fact on the side there. Anyway, so we've got contrast 1 and contrast 2. Unfortunately I've got a typo in there as well. You can tell these are new slides which I haven't made corrections to yet. So contrast 1 and contrast 2, the first contrast is significant, the second contrast is not significant. So what that's saying, remember what our, do we have it here? No, it's up here. Let me go up here. So the first contrast, this one, is significant, so the puppies are significantly, they do significantly affect happiness scores compared to the control group, so that's a significant comparison. But there is no difference in this case between the 15 and 30 minute puppy treatment. Alright, so 30 minutes isn't much better than 15, or it's not significantly better than 15 minutes of puppy therapy. You do have to look at, I don't actually have those numbers here, do I? So you do have to make sure you look at your table. We did look at the figure, or the table with your descriptives, to make sure you know which group is actually has higher happiness scores or lower happiness scores. So in previous weeks we've included the bar graph, which shows who's higher than the other, and I recall that the control group has had the lowest happiness levels, followed by the 15 minutes and the 30 minutes. So the 15 minutes and 30 minutes were not significantly different, but because we know that they are higher happiness scores, we can say that the puppy school, the puppy therapy is significantly better, or increases happiness scores significantly more than the control group. Alright, running out of breath. So hopefully that makes sense. That's the orthogonal contrasts. If you're going to do planned contrast, orthogonal is the way to go in my opinion. If you're doing non-orthogonal ones, you can do them. We're going to talk about those next. So non-orthogonal contrasts are contrasts that are related. So we talked about chunking the data out into different things. For puppies data, contrast compared to control groups, each of the puppies groups separately. Didn't really explain that very well. So basically, a non-orthogonal version of what we just did might be that we compare the 15-minute puppy group with the control group, and then we compare the 30-minute puppy group with the control group. So in that case, that control group has been used twice. Their data has been used twice in two comparisons. So it's non-orthogonal. So now we have to make adjustments for these multiple comparisons. So the same chunk has been used twice in that case. So it is okay to use non-orthogonal contrasts. You just need to make those adjustments. So the most common adjustment to make is a Bonferroni adjustment, and basically what you do with that is you get your alpha level, 0.05, and you divide it by the number of tests you're doing. So in that case, in this example where we compared each of the puppy treatment groups to the control group, we've got two contrasts, so we divide 0.05 by 2. So our new alpha level is now 0.025. So now we need to have a result below this number to have a significant effect. That's the adjustment we've made. Alright, and you can see again, we have some little comparisons down here, or some examples. If you have 4 comparisons, your new significance level is 0.013, so you have to get a p-value below that to have a significant result. If you have 8 comparisons, it's getting lower and lower, so 0.006, they're just examples. So the more tests you do, the more tricky it is to, or the less power you have in finding an effect if there is one. That's controlling for our type 1 errors. Hopefully that makes sense. And that's what our non-orthogonal contrasts look like. So comparing the control group to 30 minutes, leaving at the 15 minutes, and then comparing the control group to 15 minutes, leaving at the 30 minutes. So SPSS won't make the adjustments, you have to make the adjustments yourself. Cool. Alright, so this is probably a good point if you want to go stretch your legs. So probably a good point to pause the recording, stretch your legs, make a cup of tea, do some push-ups, run around the block, all that kind of stuff. For the rest of us, if you're not having a break, we'll continue. If you've already run around the block, we'll continue as well. Alright, post hoc tests. I think this week's going to be a little bit shorter than previous weeks, so we don't have too much longer to go. Post hoc tests. So these are, let me just read what we've got here. Often people don't have a specific a priori predictions about the data they have collected, and instead they rummage around the data looking for any differences between means that they can find. It's a bit like p-hacking. So p-hacking, if you don't know what that is explained in field 3.3 section, except that you adjust the p to make it harder to find significant differences. So p-hacking is just looking for a significant result amongst all the data without having hypotheses about it or having predictions about it, which is frowned upon, because if you just keep looking for significant results in a whole bunch of analyses, then you're bound to find one. It just doesn't mean much if you haven't set out to find that kind of difference, in a nutshell. So post hoc tests will perform pairwise comparisons, but they are performed on all possibilities. So they do, in order to find where the differences lie, there's just a number of comparisons between all possible pairs, but we will make adjustments, or SPSS makes adjustments for you. So post hoc tests do the work in the back end. So that is, they make adjustments for Familywise error in the back somewhere, so that the alpha level remains at 0.05. So when you run post hoc tests in SPSS, the beauty is that you set it up to run that, and you still use the alpha level of 0.05. You don't have to make any adjustments for that. All the adjustments have been made in the analysis, and we don't have to ever care about that. I don't really know what they do in most, and every post hoc test is different, so I've no idea what most of them do in the background, but they make adjustments with different types of statistics in the background, which maintain our alpha level at 0.05. So here's the decision-making criteria to select the most appropriate post hoc test for you. So just so you know, SPSS actually has 18 different types of post hoc tests. So here's some decision criteria, some things to keep in mind when you're choosing which type of post hoc test to use. So the first thing, does it control for type 1 error rates? So basically that's what they're all for, is to control for type 1 or type 2 error rates. There are options, if you leave it completely blank, no, you don't leave it completely blank, you do least square, I can't remember what it was called. There is one, it's in the field somewhere, I can't remember what it's called off the top of my head now, but it actually makes no adjustments, so it's not really a post hoc test, it's a fake sort of thing, but you can tick the box. I'll show you what it is in a moment when we get our little window up. But besides that, the rest of them will all make adjustments, and they'll be controlling to some extent for type 1 error, to different extents depending on the test you're choosing. So that's the first thing we're doing, making sure that our Familywise error isn't having a big effect, and that we're controlling for any chance of finding an effect when there isn't one in the population. Second consideration is, does the test control for type 2 error rate? So this is more about, does it have good statistical power to still find a significant result or a significant effect if it does exist in the population. So although we want to control for the type 1 errors, we also want to try and maintain a certain amount of power so that we can find an effect if an effect does exist in the population. And the third consideration is the test robust? So does it perform well given the conditions of the data? So if we've got violations and assumptions, or if we have big samples, small samples, unequal samples, all those types of things, is our test robust against the conditions of our specific data? So a little tricky thing about it, often criteria 1 and 2 are a bit opposed. So as type 1 error rates or chances of a type 1 error increase, the type 2 error chances go down, and vice versa, but just different degrees depending on the test you're looking at as well. We're not looking at numbers for any of those things. We just take the advice of field and others in picking which one's the best for our different conditions. So we don't have to do any crazy calculations on these things, but they're things that are considered to be true, so we follow other people's judgment on those things. So also, unfortunately, there is not a single post hoc test that is robust under all conditions. So basically there's not one test which is one size fits all. You have to sort of make a decision depending on what kind of data you've got and if you want to be a bit more conservative or a bit more liberal in your outcome, if you want to control more for type 1s or type 2 errors. Alright, so I've got a bunch of recommendations coming up. I didn't know I had a blank screen here. Oh, look at that. I didn't know I did that. Maybe someone else did it for me. Alright, so if you've got homogeneity variances and equal group sizes, so basically if everything's fine in your data, your assumptions are all good, and you have equal group sizes, then either of these is good. So I think field leans a little bit towards the Reg WQ. And these words are just, Tukey is a person, high significant difference, what that stands for, and Reg WQ is the initials of the words, which I think we'll see in a moment. So don't worry about what those actual words mean, but just it's good to get to know when you're going to be using these kind of post hoc tests. So there are two different types of post hoc tests. So if everything's good in your data, Reg WQ or the Tukey is the way to go. One or the other. If you want to be conservative and you really don't want to have any issues with type 1 errors, then you might choose to do a Bonferroni. So it's going to be a bit more strict if you really don't want to say there's an effect if there isn't one. So you want to be tough on yourself and on your data and make sure that any results you have are very likely to eliminate any issues with type 1 errors. Bonferroni is good for that. And generally I think that's also when you've got reasonably good data. If you have slightly uneven sample sizes, then Gabrielle's post hoc test is good. So what is slightly, I don't know what the cutoffs are, but if there's not massive differences between the size of your samples, then Gabrielle's is good. If you have very unequal sample sizes, then Hochberg's or Hochberg's I'm sure, G22 is a good one. And if you have unequal variances, then Games How is the way to go. And Field goes in. I've included these very sort of vague, I guess, and just sort of general outlines. Field goes into this in a lot more detail. It talks about this over a number of paragraphs. So if you want to get more depth, and he goes into a few more, I believe. But even he doesn't talk about all 18 of them. You just don't need to worry about all 18. So with this should be enough to keep you going most of the time. Cool. So, unfortunately, post-hoc tests are really, really hard to perform. If you weren't using SPSS. So they're very easy. In SPSS, they're very easy to run. All you need to do is tick a box and you'll get some post-hoc tests results. So when you're running your one-way ANOVA, you remember before I showed you the little post-hoc button? All you need to do is click on that post-hoc button and you'll get this window, and then you'll choose, alright, I know that I've got... So normally what you do, this is not always clear as well. So normally what you'll do is run your one-way ANOVA. You run it first, you'll see if you get a significant F statistic, you'll test all your assumptions, all those bits and pieces, and then you'll decide, if you do have a priori theory, hypothesis, then you'll start running your contrasts. If you are running post-hoc tests, then you have a significant F statistic, then you'll think about the conditions of your data. Are your assumptions met? Do you have equal group sizes, whatever? And then decide on what post-hoc tests. You shouldn't really just be running all these things willy-nilly. You should really do it more thoughtfully and meaningfully to get the best results. So here you can see there's a whole bunch that we never talked about. That's the one, LSD, least square differences. So what that is basically that you're not running any kind of post-hoc. It's just unadjusted, completely liberal, no control over type 1 errors. That's the one I was talking about before. But I digress. So Bonferroni, we talked about that one, conservative one. Reg WQ and Tukey, they're two that we talked about if your conditions are all good and you have equal sizes. Hochberg's, if you've got unequal sample sizes. Gabrielle, if you've got slightly unequal sample sizes. And then the Games How is down here if your equal variances are not assumed. Now there are other ones here, and if you want to read up about them and figure out if there's better options for you, you can. But if you know those ones that we've talked about, that is sufficient for this unit. You can see it's got the significance level. I've never adjusted this in my life, so you shouldn't have to do that either. So very easy to run the post-hoc tests. This is the kind of output you're going to get. So there's two main types of tables that you get in a post-hoc test output. Mainly you'll get this top table, but for some of the tests you'll get this bottom. So Tukey actually gives you both types of output. So how do you interpret what's going on here? This is how you interpret it. So these red arrows will show us all we really care about. So you can see this first sort of couple of rows, I guess, is comparing the control to the other two puppy groups. The second bunch is comparing the 15-minute groups to the control and the 30-minute groups. And then the bottom section is comparing 30 minutes to the control and 15 minutes groups. So you'll see that there is a lot of redundancy in here. So we really only care about 3 of these comparisons. So, and I've marked them out with our red arrow here. So first, if we look at control versus 15-minute group, we look along that line, we have a p-value of 0.516. So there's no difference between the control group and the 15-minute group. Look at the control group versus the 30-minute group. Come across here, look at the p-value. We do have a significant, it's less than 0.05, so we have a significant difference. So 30 minutes is significantly different to the control group. Again, you have to make sure you check your descriptives to make sure you know which direction that's going. But because we've already looked at the figures before, we know that 30-minute group has higher happiness results than the control group. Again, there's the main difference. So this says I minus J. So if we get the group I minus this group J, we end up with a negative score. So this is saying that the control group is lower. And then the standard error, blah, blah, blah. You don't have the T statistics or the degrees of freedoms or anything to report here. So all you need to do is report the p-values when it comes to reporting these. We do have the confidence intervals. Again, we haven't talked about them yet. We'll talk about them a little bit later on in the unit, but for now we'll just leave them out of it. So so now we've compared the control group to the two puppy groups. Last comparison we need to look for is the 15 minutes versus 30 minutes, and here we've found that there's no significant difference between these. And the reason we don't care about the other ones is 15 minutes versus the control is exactly the same as what we've got at the top, and you'll see the p-value is exactly the same as well, so it's redundant. We don't need to keep reporting the same thing over and over again. And then we've already compared the 30 minutes to the control group up here, and then 30 minutes to the 15 minutes here. So again, these two p-values are reported up here. So only half of the output in this case are of interest to us. And that's all I've written down here, I believe. Cool. So hopefully that makes sense. It can take a bit of time to get your head around how to interpret these output. When you start breaking it down, it really does make pretty good sense, and it's quite easy once you get used to it. But I'm aware that initially looking at these things, they can be a bit confusing and overwhelming. So again, when you start looking at your output, just take a few deep breaths, get into the zone. Make sure you don't block yourself by saying I'm no good at stats or anything like that. Take your time and start working your way through the tables. And practice. That's what it all comes down to, really. We'll do this in the tutorial as well. So the second type of table that we there we go. I've just got the p-values down here that we looked at. So the second type of table, I've talked a lot about this. Probably don't even really need to know how to read these tables. I don't know, or maybe you do. There might be a post-hoc test or two which only gives you this type of table. I'm not sure off the top of my head. So the below table says the same thing but in a different way. So this is the same type of analysis, still a Tukey HSD. Here you can see that we have homogeneous subsets. So that's what these red cells are. They're known as homogeneous subsets. Alright, so that is the mean scores of the groups within each box, or the subsets, are not statistically significantly different from each other. They're homogeneous. So here control and 15 minutes are homogeneous, and 15 minutes and 30 minutes are homogeneous. So if you look, we've got the control group here. That's just their mean score, and the 15 minutes mean score. They're homogeneous, and there's no significant difference between them. And we can see that this is the p-value between those two. And that should be, you can see it's the same p-values we have up here. And then we have the 15 minutes group and the 30 minutes groups. P-value here, 1.47. There we go, it's the same one up there. So they're not significantly different. But because the 30 minutes and the control are not in the same subset in any case, then we know that there's a significant difference between them at the 0.05 level. So it's not telling us anything more really than what we can see up here. I much prefer these ones, but sometimes it's a nice little visual just to get your head around what's going on. Alright. So generally, you better, and it's always nice to see the p-values too. We talked about the null hypothesis significant testing last week and its flaws. So knowing the p-value is quite important in interpreting what's going on. So you're much better reporting the actual p-values rather than saying just p is less than 0.05. So if this is available, use the actual p-values. So that's post hoc, and all the other post hoc tests will have something similar to this. Most of them have a table like this. If you put in multiple post hoc tests, then you might end up with rows and rows of these types of comparisons. And then some of them have this kind of, I think Reg WQ is another one which has subsets. Yeah. So here's an example of what the write-up might look like for planned contrast. So a lot of this stuff we had in from last week. We wrote this all up last week. So we go on through, we said what's going on, referred to again last week I said that our figure's getting smaller and smaller. It is getting smaller and smaller. You'd never include a figure that small in your write-up. I just need to fit it all into one slide. So we've got referred to the figure. We talked about our assumptions. We did all this last week. We said our one-way ANOVA was significant. We reported that and included the effect size, which we talked about last week as well. And I think that's still a wrong F statistic. Anyway, so now this is a planned contrast version. So planned contrast revealed that the puppy therapies increased happiness compared to the control group. So remember, this is our contrast. The first one was just comparing the puppy therapies to the control group. There's our statistics for that. And that there was no significant difference in happiness scores between the groups participating in the 15 minutes and 30 minutes of puppy therapy. And there's our T statistic for that. On top of that, we should really, which we didn't include here, remember we should be interpreting our effect size. So saying that this is considered a large effect size according to Cohen, 1988. And then the other thing we should do is, which I don't think, we did do it here. So here we've said that you need to make sure that you are saying how the difference, not that there just is a difference, but what the difference is. So here we can see that the puppy therapies increase happiness compared to, that's a bad sentence too anyway. But it's saying that puppy therapies has a more of an increase on happiness than the control group. So make sure you are clear about which is having the more greater effect. You know, is one significantly higher or one significantly lower, or vice versa. Yeah, so just make that clear to the reader. Cool, and we'll unpack this heaps more in the tutorials. So if any of this stuff still isn't making sense, bring your questions along to tutorials. We'll have good discussions and make sure we're all happy with all these things, and we'll write these out in a bit better format than what we've got here. There's two reasons why it leaves a bit to be desired in our write-ups here. For starters, we don't want to give you, we want you to work a little bit to get your writing up, so we don't want to give you the perfect write-up, and there also isn't really a perfect write-up. There's lots of really good ways of writing up these things, and there's also a lot of poor ways of writing them up. So we want you just to be able to work it around yourself. And remember, this is all written in English, even though there's some weird words in here. It's still in English, so it just needs to make sense when you read it out. So we just leave a little bit to be desired in how we write these things up. But the second thing is that they've been written a little bit hastily, probably. Either way, we'll make sure that you write them up better than it's been written here. So here's a post hoc test write-up. Everything's the same except after the F statistic here. So we've reported the one-way ANOVA, and then we go Tukey HSD adjusted pairwise comparisons reveal that there was no difference in happiness scores between the control group and the 15-minute puppy therapy group. P-value, so see how I've just included the P-value in the brackets there. or between the 15 minutes and 30 minutes of puppy therapy, p-value here. There was, however, a significant difference between the control groups and the 30 minutes of puppy therapy, p-value. You might also notice that there is a difference in how these were interpreted compared to when we're doing post hocs or planned contrast. So the planned contrast is saying that the puppy therapy is having more an effect over the control, both of them, where this one's saying 15 minutes isn't having that much more of an effect, but the 30 minutes is having more an effect over the control group. And that all comes down to, there's all different kinds of stringencies and different, whether they're more conservative or more strict. But also, because these are orthogonal, we didn't have to adjust for any comparisons, so it's more powerful to find the differences. Alright, so hopefully that makes sense. That's all we're going to do today. So that's basically the end of, besides the tutorials this week, that's the end of one-way between groups ANOVAs. So we've spent, week 4 now? We've spent 3 good weeks on fully unpacking one-way between groups ANOVA. In next week we're going to go on to doing a factorial from memory. I haven't done those lectures yet, but I think we're doing a factorial between groups ANOVA. And then after that we're going to get into repeated measures, where we start mucking around with the same groups being compared over different time points, and then we'll get onto some other analyses over that. But that's the end of the one-way between groups ANOVA 3 weeks, so hopefully it's making sense to some extent how you would run this kind of analysis in its entirety. And you know what's going on to some extent. So it might be a good time just to really go back over these things and remember what's going on. Remember we need to figure out the assumptions, make sure the data is in a good way for us to run the analysis. It's good to know what's going on underneath the ANOVA itself. So we've talked about the variance and how it's partitioned, how we're doing the comparisons, and then we can talk about the effect size, how much of the variance is being explained by our model, and we follow it up with these post-hoc tests or planned contrasts to figure out where the actual differences are. So there's 3 major steps, and they will run pretty much through all the different types of ANOVAs that we'll be doing in this unit. So we definitely spent a lot more time on that. More time on initially just to get our heads around it, and the future ANOVAs are not going to spend quite as much time working on them. It should make more sense. So recap, we've talked about Familywise error. Again, you don't need to be able to calculate that, but you do need to be aware that it can be an issue if you just run a bunch of different comparisons. So we don't want to be making type 1 errors all the time, so we want to make sure we're aware and try to account for Familywise error, make adjustments, or do planned contrast so we don't have to worry about it. Planned contrast, we talked about these in a lot of detail. Post hocs, we probably didn't unpack these as much as we could have, but really you don't need to know what's going on underneath them. It's really about just remembering which ones, or not necessarily remembering, but having a nice go-to list of which one you're going to run in certain circumstances, depending on the conditions of your data. And then we've further developed our writing up of the output of our entire one-way between groups ANOVA, from the descriptives to the assumption testing to the F statistic itself to the follow-up tests. Cool. So Statman says, make sure you know how to report your results. So it is important to make sure you do follow the strategies that we're providing for APA write-ups. As far as the structure and all that of your result sections go, you can play with it a little bit. It's not that it's set in stone completely, but probably at this stage it's just as easy to follow the structure. Maybe talk about your descriptives a little bit, or allude to a figure first, talk about your assumptions, talk about your ANOVA, and then talk about your follow-up tests. It just makes sense to go in that order. It's not that it's strict like that, but until you're getting to a bit more, increasing your expertise in statistics, then it's probably just as easy to follow that kind of structure. And that's all we have. So I'll say good night, or good day, or good evening, whatever you might be doing at the moment, and I'll see you in the tutorials. So I hope that was fun. Alright, see yous.